we're going to talk about limits and continuity in the complex plane. I encourage you to look at the definitions of limit and continuity as we go along here. But intuitively, what happens is if you got this point z naught, and we're going to look at the limit as z approaches z naught. It's not really legible. Of f of z is equal to, how about some point L is what we're going to call it. Maybe L's down here. Now, this is a little more complicated than regular old calculus, because what can happen is that you can't just, there are more than two ways to approach z naught. You can't just approach from the left and from the right. You can approach from kind of a curvy point like this, or you might approach from something like that, or you might approach like something complicated like that. But for right now, let's just kind of assume maybe we approach something like this. So as we approach, we're going to have like a z1, z2, z3, and we're going to see what happens over here. Now, as you map it over, hopefully, if the limit exists, the way you want to think about it is that there's some other path, and who knows what it is, where you have f of z1 might be right there, f of z2 is right there, f of z3 is right there, and they're getting closer and closer and closer, kind of as a general trend. You might have, like, maybe z3 ends up out here, but z4, z5, z6 all get closer to L. That's kind of intuitively how you think about it. As you get closer to z naught, you get closer to L over here. Technically, what you want to think about is the definition. The definition says, okay, let's not think of this as a process. Let's just think of it as, is it possible to get within a circle of epsilon of L? Can I get close enough to z naught where if I'm close enough to z naught, I'm guaranteed to be that close to L? Well, yeah, so the idea is if you can draw, this is what they call delta. If for every point in here, in this little ball, you end up mapping into this circle, and that's true for any epsilon. So they give you an epsilon, you have to come back with a delta where anything in here maps over to there. That's what we mean by a limit. So that's the definition of limit. And very roughly speaking, I'm going to give you an example that should help clarify that. So very roughly speaking, if L equals f of z naught, we say f is continuous. So basically continuity is roughly just where the limit is the function value. So as an example, I'm going to look at f of z equals 2z plus 1. Z naught is equal to, how about 5? So let's just draw a quick graph of this. So here's 5. I'm going to map over with my f. Well, 5 is going to map to, let's make this 2z plus I. So 5 will map over to 10 plus I, which this is not to scale. That'd be f of 5. And I'm going to show you that this delta epsilon thing holds. So I said you need to be given an epsilon. So I'm going to give an epsilon. If epsilon equals 1, how close do I need to be, right? So what I can do is I can say f of z minus 10 plus I has to be less than epsilon. Can I do it? Can I make sure that I'm within the circle? Well, yeah, if I just plug this in, I get 2z plus I minus 10 minus I has to be less than epsilon. In other words, 2z minus 10 has to be less than epsilon. In other words, 2 times z minus 5 has to be less than epsilon. And so whenever z minus 5 is less than epsilon over 2, I will be guaranteed to be within there. So let delta equal that, and we're done.